Okay, so on this segment, last segment of this chapter, I would like to just do one problem here. And it might be just a short segment. So we have an exercise machine. This problem comes straight from the book, the very last problem in chapter 10, or example from chapter 10. An exercise machine at a gym has a weight of 5 kilograms attached to one end of a horizontal spring with force constant K equal to 80 newtons. The other end of the spring is anchored to the wall or to a wall. When a working uh, when a work actually it should say when a woman is working out on the machine pushes her arms forward. When a woman working out on the machine pushes her arms forward, a cable stretches the spring by dragging the weight along a track with a coefficient of kinetic friction of 0.3. And then it says, what is the woman's power output at the moment when the weight has moved 50 centimeters if the tension is a constant 100 newtons? Here it should say when a woman is working, oh, a woman. So, okay, so let's draw it so that the details of the problem become clear. Here's a wall. Here is the spring that's anchored to the wall. Here is a mass that's attached to the spring. Mass. There is friction. Friction here. So what happens is, let's say this is the initial position. So now our system will be the spring plus mass. There is the force. So what are the forces external to this system? What are the forces external to this system? Let's draw them. The spring and mass are interacting with each other. So we will have kinetic plus potential energy of the spring. And so what are the forces? There is the force of the wall that's external to the spring, but it's not doing any work. So we don't care about it. There is the normal force upward, but it's not doing any work. So the work done is zero because the woman will pull the mass this way, and so the motion is this way. So there is a 90-degree angle between the normal force and mg. So that both of these, the mg and the normal force, will do zero work. Now, who's doing the work? The tension when the woman pulls on the cable or whatever it is, the force of the woman this way, let's call it tension. And then there is the force of friction here. If you move to the right, there is force of friction to the left. So we will say that the energy at the end minus the energy at the beginning will equal to the work done on this thing by those non-conservative forces. We have two of them. The tension in the cable, the woman has an external force pulling, so right? Imagine, how do you exercise? You eat calories and then you pull things, and so that gives you energy. And so that energy is non-conservative. It's an outside. And then we have the force of kinetic friction is also non-conservative. So it would be the work done by the force of friction plus the work done by this tension that pulls. Okay, and we're going to pull the mass to here. The initial speed of the mass is 0, and I wonder what the speed here will be. Okay, so let's see. The energy will be, you will have kinetic plus potential, kinetic plus potential. The energy at the end will be the kinetic energy in the mass, so that's 1/2 mv final squared plus, and then minus stuff, and then equals, right? The energy at the end will be the kinetic energy in the mass plus the potential energy in the spring, 1/2 kx final squared. And then minus the energy at the beginning, that's the kinetic energy in the mass, 1/2 mv initial squared, plus 1/2 kx initial squared. Now, the work done by friction will be, let me write it here, the work done by the force of friction will be the force of friction, which is mu k times the normal force, and the normal force is mg, that's the force of friction, times the distance moved, which is how far we stretched it, so that's x, and then times the cosine of the angle, but that's cosine of 180 if you remember, so there is a minus sign. The work done by the tension will be the force of tension, so that's T, times the distance moved, that's x, and the tension is this way, the motion is this way, so the cosine is, it's the cosine of 0 degrees, so that's 1, so it's just T times x. So here I have negative mu k mg times x, and then the tension times x. So let me factor the x out, so plus tension, and then the whole thing times x. The mass is not moving at the beginning, so that's 0. The spring is not stretched nor compressed at the beginning, so that's 0. 0. Okay. So now, we need to find the speed. So let's multiply both sides by 2, both sides by 2, so we'll have mv final squared plus k x final squared equals, this part was 0, is equal to t, I'll put the t first and then minus mu k mg, oh I multiplied by 2 so there is a 2 here, and then there is the x. And x, by the way here, x final is x, because x initial is 0 and x final, let me just call it x, and I will drop the final thing here, first x, I'll drop the final, the subscript final. I will keep it here, but then drop it here. Drop it here. X final will simply be 50 centimeters. So I have, let's solve for v. So we'll have, we will move this to the other side, divide by the mass, and solve for v. So we get v final will be the square root of what? Divide everything by the mass, so you have 2. I'll put the x in front, and then t minus mu k mg divided by the mass. And then when you move this to the other side, it becomes negative kx squared, but we divided by the mass, so there is the mass here. So, in fact, let me just extend this with the minus sign here, and put them both under the common denominator. So let's plug in the numbers. X is 50 centimeters, so that's 0.5 meters. Let's get V. So I have 2 times 0.5 times. The tension is a constant 100 newtons, so the tension will be 100. Minus, I will not forget the mu k in this problem, 0.3. Remember earlier I forgot it in the previous segment? Times the mass. What's the mass that's moving here? It is, I forgot how much was it. Has a weight 5 kilograms times 5 kilograms times g, that's 9.8, and then minus kx squared. K is 80 times x squared. X is 0.5, so 0.5 squared. And then we have to divide everything by the mass, which is 5 kilograms here. Is it 5 or 50? Let me make sure I didn't make a mistake. Yeah, it's only 5 kilograms. So I get that. Then we have to take the square root. And I get the speed to be 3.61. The speed is 3.61 meters per second. You might say, nobody asked you to find the speed. We were asked to find the power with which the woman is exercising. How much energy is she giving off at this point? Well, remember, power was the rate at which you give off energy, the work done per second. And the work done per second is the force times velocity. It's her force times the velocity. So the power from the woman will be the force of the woman, which is the tension, times the velocity. The tension is 100 times 3.61, so that will be 361 joules per second, which is 361 watts. All right, so let me just double check that I have it correct. Yeah, about 360, 361. All right, so there you have it. The next video will be on end of chapter problems from this chapter 10, and then we're ready to start momentum, which is chapter 11.